Picture a coffee shop at dawn. Steam curls, orders bustle, and for a fleeting instant, the cup in the barista's hand is both latte and espresso. Two equally real possibilities hovering in porcelain. That is superposition, the most famous party trick of quantum physics. But if a single footstep rattles the counter, the spell collapses. The drink chooses. For 30 years, our boldest engineers have tried to harness that fragile both-at-once state. Convinced it could solve problems no classical computer can touch, now on laboratory benches chilled colder than deep space. The next chapter is unfolding one that reaches beyond superposition and toward a woven tapestry of quantum effects. Each strand essential, each at risk of unraveling. First, we need to meet entanglement and interference, the real power couple of the quantum realm. Imagine two violin strings tuned not to the same note, but to the same destiny. Pluck one, and in a soundproof room across the city, the other vibrates in sympathy. Entangled qubits share that uncanny bond. Yet the music becomes thrilling only when we add interference. Artful overlapping of probability waves so that some outcomes reinforce. Others cancel, and the solution we seek rings through like a pure chord. A quantum algorithm is less a sequence of commands than a choreographed dance. We set the initial pose, let entanglement and interference swirl, then freeze the motion at just the right beat to read a single, definite answer. But choreography demands a stage, and today 9 rival stages jostle for the spotlight. In California and Hufei, scroll-thick aluminum circuits nestle inside dilution refrigerators. Here electrons tunnel through Josephson junctions, creating superconducting qubits that flip billions of times a second. Their great advantage is speed, their Achilles heel is noise. Meanwhile, trapped-ion platforms, from Maryland to Innsbruck, levitate strings of calcium or terbium atoms in electromagnetic cages. Lasers tickle each ion, coaxing logic gates with record fidelity, though the pace is measured in kilohertz, not gigahertz. Neutral atom arrays gather rubidium like beads on an invisible loom, rearranged by optical tweezers into checkerboards as wide as a postage stamp. Spin qubits in ordinary silicon promise seamless marriage with existing fabs. Photonic chips guide single particles of light through glass mazes at room temperature. While a handful of theorists still pursue topological qubits, information braided into exotic states of matter that would shrug off local disruptions as a rope shrugs off a gust of wind. Every approach is a different wager on how to tame the restless quantum sea. Yet whichever hardware prevails must confront the same storm. Error, a cosmic ray, a stray microwave, a rumble of mechanical vibration. Any can collapse superposition in a microsecond. The solution is counterintuitive. Embrace redundancy. Instead of storing one logical qubit in one physical device, spread it across dozens, even thousands, stitching them together with an error-correcting code. Picture a leaky canoe. Water seeps through every seam. Your only hope is to add planks faster than the leaks appear, building a second hull around the first. In 2023, researchers at Google and later at Yale demonstrated early versions of that strategy. Increase the number of physical qubits, watch logical error rates drop. It was a modest craft still far from ocean-worthy, but proof the wood can be laid faster than the water rises. There is poetry in this. The quantum computer will not be a jewel box of perfect silence. It will be a bustling organism, errors constantly born and constantly repaired, like DNA in a living cell. And when, sometime in the 2030s, engineers finally unveil a fault-tolerant machine with perhaps 100 logical qubits, its first triumphs may surprise us. Chemists yearn for exact maps of catalytic reactions blueprints for carbon-neutral fuels. Material scientists dream of batteries whose ions navigate crystal lattice with the ease of fish in water. Cryptographers prepare for the day Schur's algorithm hums through prime numbers that underpin today's internet security. All these challenges hinge on the exponential complexity of quantum states. Jungle too dense for classical machetes, yet native ground for a machine that grows stronger as entanglement deepens. But computation is only chapter 1. Across the Netherlands, a fragile quantum internet already links 3 nodes, teleporting qubit states through entangled photons. In South Korea, a quantum gravimeter senses subterranean tunnels by measuring how entanglement shifts in Earth's field. These devices explore an insight more radical than any headline algorithm. Quantum information is a currency that can flow, trade, and secure value even when the messages themselves are undecipherable. Privacy by the laws of nature. Of course, every glorious roadmap demands a reality check. Moore's law. The gentle doubling of classical transistor counts was powered by well-oiled supply chains and predictable physics. Quantum technology advances in pulses. A sudden increase in coherence time here, a fabrication breakthrough there. Venture capital surges, retreats, then surges again. Governments fund national labs, while garage startups tinker with photonic chips no bigger than a coin. Ask when we will reach quantum advantage for general tasks, and the honest answer is, when the noisy, error-prone prototypes shrink their faults by 2 orders of magnitude and their qubit counts by the same growth. Optimists see a decade. Realists hedge longer. Yet pause beneath the mountain of technical acronyms, and you'll feel a simpler wonder. At its heart, the quantum computer is an invitation to imagine reality as malleable pattern, not immutable stuff. We are learning to paint with probability amplitudes, to sculpt with interference, to weave with entanglement tools, once relegated to philosophical footnotes, now soldered onto circuit boards and etched into silicon. The leap mirrors the moment when early humans chipped stone into blades. Mastery over a realm, previously navigated only by instinct. So where might beyond superposition lead? Perhaps 2 hybrid machines, where classical cores handle control logic, while quantum coprocessors tackle molecular orbitals. Perhaps 2 distributed networks of modest quantum nodes, stitched by photons into one collaborative engine. Or perhaps the ultimate breakthrough is still hidden in topological braids, in microwave cat states, in error-corrected qubits that store more than 2 levels per site. Whatever path unfolds, the goal is constant: to keep the quantum melody playing long enough, loud enough, and pure enough that we can hear the solutions hidden in its harmonies. As we end this crash course, let the takeaway rest on a single sentence. Superposition opens the door, but entanglement, interference, and error correction carry us across the threshold. The future of quantum computing is not one trick, but an orchestra. Each instrument fragile alone, majestic together. And we, the audience, sit poised for the first full symphony. This is cosmic canvasware. The universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.